Good afternoon, everyone. So as Paige mentioned, today we are going to talk about evaluating LLMs and potential pitfalls. First, I'm going to give a broad overview of LLM evaluations. I'm going to answer your basically your WH questions, like what is evaluation, why do we need to evaluate, when do we evaluate, and how to evaluate. And I'm gonna also provide one specific example. Then we are going to break you out into rooms where you will brainstorm on specific predefined use cases. After that, you are going to report back to us in the main room, and we expect to have a discussion about what you think, the evaluation techniques, strategies you thought about, and what you think could be done or should be done about evaluation. Then Bethany, that you already know, like I think she did session 2, will talk about current methods and limitations. And then we are going to end this session and this series with Sandeep with his science talk. All right. So what is LLM evaluation? A generic definition is that LLM evaluation is the systematic process of assessing the performance, capabilities, and trustworthiness of your large language models. So things to evaluate for, this is a non-exhaustive list of things to evaluate for. They include accuracy, efficiency, robustness, but also all of the safety, privacy, and ethics categories, and as well as fairness, diversity, and bias. So this list is non-exhaustive, and depending on your application, you might want to evaluate something that's not here. Evaluation is important because it allows you to measure how well your LLM is performing on a specific task. So you can do performance benchmarking with evaluation. With evaluation, you can see if your LLM is performing as intended, and you can identify unexpected or undesired outputs. With evaluation, you will be able to know the areas where your LLM works well and where it struggles, and maybe what you should do, what refinements you should do about that. What is increasingly important and that have been making headlines about LLMs are like the safety and ethical considerations. You want to evaluate your LLM for potential biases. You don't want your LLM to enhance, to reproduce bias. You don't want it to output harm, to give harmful outputs. And especially for sensitive applications like in medicine, finance, I don't know, or defense, you want to make sure that your LLM is compliant with legal and regulatory standards. So during the first weeks of this series, you've learned about pre-training LLMs, which is like the first steps of the LLM pipeline or workflow, if I can use those terms. That's when you train your LLM on text data to predict the next word in a sentence. I don't know if you remember the first science talk that Arvin gave. He presented the genomic/language model, GenSLM. So pre-training for that model would be when you train it to generate genome sequences. So when you do pre-training or after you do pre-training is a good step to do some initial evaluation. So in that step, if you do it, then you are evaluating for the qualities of your LLM outputs. For GenSLM, that would be, for example, evaluating the diversity of the sequences generated. You want to make sure that GenSLM is outputting sequences that are as diverse as your initial or training or real data set. You want to make sure that you are getting sequences like you are outputting the different protein sequence, the different protein families in your real data set, and within each family, you have to make sure that you are reproducing the different isoforms or like folds. You've also learned about fine-tuning, which is when you adapt the model to a specific task. I know Arvin talked about how GenSLM was fine-tuned to predict COVID variant. So after fine-tuning is also a good step to do some evaluation. So here it would be assessing how the fine-tuned model is performing on the specific task. Now, how do you evaluate LLMs? So you can divide evaluations of LLM into two categories. Basically an automated one and a not automated one. So not automated usually involves a human in the loop. So meaning that you have an expert that can assess the quality or the correctness of your LLM output. As you can imagine, that can be pretty slow or inefficient. So you also have like automated strategies. So within the automated category, you have two subcategories, what is called the intrinsic evaluation. This is when you evaluate the inherent properties of your large language model. That would be evaluating how well it predicts the next word. That would be assessing its fluency, its coherence, like seeing how it compares to reference text. And you have, or for the case of GenSLM, like seeing how diverse it is. So you have different metrics for all of these different evaluation tasks, like the Venn score for diversity or the blue score for assessing things like fluency or coherence. You also have what is called extrinsic evaluation, which is when you assess how well your LLM is doing on a specific task. So this can be done through question answering, sentiment analysis, text summarization, or again, the blue score. So for the blue score is a widely used metric for evaluating LLM. It's pretty easy to compute, but you can see in this example here, so this is translating a French sentence. So the reference translation is, the teacher arrived late because of the traffic. And depending on the max length of n-grams you are considering, I believe n-grams were introduced to you earlier in this series, you have different scores. So of course, you're gonna have the best blue score for the translation with words that are in the reference text. But you can have also very low scores for translations that are actually quite good, but use different words. So for cases like that, to avoid like penalizing such translations, it can be good to have, for example, a human expert that could like maybe gauge the quality of a translation. So in the literature, evaluation is actually done using benchmarks. So you have a big sets of benchmark with batteries of tests, and then that's what you use to evaluate your LLM. I'm just going to talk briefly about a couple of these benchmarks. One of the first one is the GLUE benchmark, which consists of question answering text. So you have questions and you have the answer, and you just want to check that your LLM is like reproducing the correct answers. You also have SQUAD from Stanford, which is good for evaluating reading comprehension. As the name indicates, it's a question answering dataset also. Recently, researchers from UIUC, they are actually now at the University of Chicago and at Argonne, came up with decoding trust, which is a comprehensive assessment of trustworthiness in GPT models. So they look into things like fairness, toxicity, stereotypes, bias, and like have different scenarios and different metrics to evaluate LLMs for this metrics. And then you have HELM. So HELM is for holistic evaluation of language models. It's a pretty complete framework with different domains that can be evaluated and different metrics. And I'm going to show an example using HELM to evaluate the Llama 7B model and also the Claude 3 model on a specific task. So as I said, HELM is a pretty complete framework. It provides a standardized multi-metric. So they provide like 7 metrics like accuracy, robustness, bias, like to evaluate language models. And for each metrics, they have like, you can choose from 42 scenarios ranging across different domains like books, news, math. So you can actually see if maybe your LLMs will be good at math and be very biased, like very stereotyped. So you want to evaluate all of these things. So the scenarios they use are divided into 2 categories. So they have 16 core scenarios. That would be your question answering, summarization, like information retrieval. And they also have 26 targeted scenarios. So that's for like deeper analysis, for like checking reasoning, knowledge, and this information. So the example I'm going to show today is on reasoning, specifically math reasoning. I'm going to use the math benchmark dataset. So it has like more than 12,000 challenging competition mathematics problem, and each problem has like step-by-step solution. So as I mentioned, I'm going to evaluate the Llama 7B and the Claude 3 model. So you can actually go. Bethany found this great website where you can you have one place where you can try different models. So chat.lmsys.org. And I'm gonna use that's where I did my evaluation. So to access the data set, you can go to the HELM website and then click on scenario and then scroll down to math. So the data set looks like this. It has like several requests. So one such request, so this is from the algebra subset of the data set. So you give a prompt, like given a mathematics problem, determine the answer, simplify your answer as much as possible. And then you give a suite of problems with their detailed answers. So these are like, I took the level 1 algebra. So these are like pretty easy problems. Like, for example, like compute 95 square, things like that. And then the LLM is asked to solve the last problem, which is the sum of 2 numbers is 40 and their difference is 12. What is their product? So first I tried, I asked Llama 7B to solve this. I gave it the same request like 10 times. And it never got the right answer. So it would confidently tell me like the answer is 48 or 784 or like 480 and consistently giving wrong answers. Then I prompted it some more. First, I asked it if it was sure of its answers, and then it said, "Oh no, you are right. I'm wrong." But then it still gave me a wrong answer. Then I asked for the steps the steps that it did to conclude, to get to the answer like 480. But then again, you can see the answer here. The mistake, it starts making a mistake here. It says that the sum of the two numbers is 40. So one number is 40 divided by 2, which is 20. I mean, which is obviously not correct. And you can see that even if it's giving me like different answers for each prompt, like 480, 240, and then 640. I manage with like more questions to make it write the question into equations, like x plus y is 40, x minus y is 12. It found like x is 26, y is 14, but it still couldn't make the product. For some reason, it can't compute 40 times 12. On the other hand, the Claude 3 model did pretty good on this task. It consistently gave the correct answer and consistently gave me detailed steps. Maybe, I mean, it was just a variation of this answer here. Maybe the words were different, but the reasoning was always consistent and the same. So you see the two kind of extremes, one model that's not performing well on like basic math question, and another one that is good on this. So this is just an example to show you what questions, like if you are interested in things like math capabilities, what questions you can use and how to prompt your large language model to show you how it's reasoning. I wanted to briefly talk about this metric, which is called the Venn score, that is used to evaluate diversity of LLMs, but specifically for science problems. So this is very adequate for fields like genomics, molecular biology, and things like that. And it's pretty straightforward. It basically needs samples. So if you have your LLM, you would give it your outputs. And you also need to define a similarity function. You don't need to know anything about the model. You don't need a reference data set. It's pretty interpretable. It just computes the Shannon entropy of the similarity matrix of your sample. And then the Shannon entropy of the eigenvalues of the similarity matrix. And then you can see here for a toy problem, when it's just one element in your sample, the Venn score is 1. Then as you add more different elements, it increases like up to 4 here. It can be pretty expensive since you have to compute eigenvalues. So it can be as expensive as n cubed, and it depends on the similarity function. It's as good as your similarity function is. But however, one nice thing is you can compute embeddings. If you have access to your LLM weights, you can compute the embeddings and use a similarity function based on the cosine similarity. So this means you can use the cosine similarity for like all models for which you have the weights. And this also reduces the complexity from n cubed to d square n, where d is your embedding size. I tried it quickly on Gen SLM. So here is the MDH, the model fine-tuned on the MDH enzyme, and this is the model trained across all the families that were considered for Gen SLM. So for the MDH fine-tuned models, using the similarity function based on alignment scores between sequences, you can see that the Gen SLM fine-tuned model is preserving the diversity according to this metric. It's like 38.5 for the training data and 37.8 for the generated sequences. But then for the generic model, you can see here, you see this is the training data. It was 132. And then for the generated output, it dropped to 100. And you can see here, like these two similarity matrices, you can see more bright spots appearing on the sequences. So I just wanted to show this to showcase that you have also metrics, though they are not that many. You have metrics for specifically science problems like generating sequences, creating, build new generating materials and things like that. So in conclusion, I have shown what is evaluation, why we do it, and how we do it. It is a critical point of the LLM pipeline. I've talked about the main categories of evaluation techniques, like the automated ones and the human-based one. You have to keep in mind that most evaluation techniques requires using reference text or like benchmark, large and comprehensive benchmark data sets. However, there are emerging reference-free methods, but they remain scarce. So for the remaining of this session, we are going to put you in breakout rooms where you are going to discuss evaluation strategies on 10 use cases, and then we are going to come back in the main room, report back on your findings, and Bethany is going to talk about methods and limitation before Sandeep's science talk. Thank you. I have like 2 more slides about evaluating things like stereotypes using the decoding trust benchmark, but it's just for your information if you are curious to see more prompts for like this specific task of evaluating stereotypes. It's on the GitHub page. Thank you.
So today we're talking about how to evaluate LLMs and also some potential pitfalls. And so I think this in this session and course, you've heard about some strengths of recent large language models, like they can handle a lot of data, and on some benchmarks, there's been a lot of progress. And sometimes they can do well on tasks they're not explicitly trained on. Some of them can produce code. And unlike some previous approaches for AI applied to language problems, LLMs generally don't require knowledge graphs, databases, labeled data, or annotating the grammar in sentences. But there are some limitations. So one is, as Carlo touched on, in large language models, we're making a specific modeling choice for the data. We're representing the data as a sequence of tokens, and then embedding those tokens. And not all data sets are modeled well by a sequence of tokens. So one example is LLMs are surprisingly bad at arithmetic. And here's just an excerpt from, I asked Claude to add these 2 numbers. And here's just the end steps. Now, overall, it looked reasonable. But if you look at step 6, it's gotten confused. It wants to add the 10,000th digits, and it's the wrong digits. And then it says to carry 1 to the 100,000th place, which doesn't make sense. But then it somehow gets the right answer at the end. Probably this model calls a calculator. So it gets the right answer, but then it can't explain how it got there. And I was surprised. You can see this is dated last week. I tried a bunch of models, and none of them could give me a correct explanation for this kind of arithmetic problem. So this is a case where I don't think this question is modeled well with tokens. So if you picture my initial prompt of asking for an explanation of how to add these numbers, and then think about how tokenizers work, and then embedding in some space, now you've kind of lost the maybe exact details of what I've said, and it's producing an answer 1 token at a time, and maybe kind of loses track of where it is in the problem. And of course, this would be way more efficient to use a calculator and, like, I don't know, read some, maybe have a formula for how to explain addition with multiple digits. You could programmatically create this explanation. LLMs are also very computationally expensive, especially if you're trying to process long sequences, because attention is quadratic in the length of the sequence. And it takes a really long time to train. These numbers are on the low side, hundreds of thousands of compute hours, millions of dollars. And then inference time, which is when you're trying to use a trained LLM, yeah, also the cost adds up. So it's a little difficult to estimate, but something like using an LLM costs 10 times as much as like a standard Google search. And using a general purpose model for a task is more expensive than using a special purpose model because you have some large model in order to cover a lot of scenarios. And people usually talk about the cost of the training time of an LLM, but inference time starts to become the bigger problem when you have a lot of users. So maybe it costs you millions of dollars to train your LLM, but the cost of the servers and electricity to handle all your customers' queries might dwarf that in a couple weeks. So they might charge us now, they might later add costs. It really adds up a lot. Okay, so an exercise could be using OpenAI's tokenizer to see how a prompt would be represented, and then think about how, if you were building a special purpose solution to this problem, how you might do it more effectively. But it's already 4 o'clock, so let's skip this for now. You could always play around with it yourself. Miriam, if you can put that link in the chat to the tokenizer. I think this overlaps a lot with previous sessions, so we can skip this. Now, a big problem with large language models is that they're not reliably accurate. And people often call this hallucinations. People talk about this a lot. The LLM is trained to predict probable sequences of tokens, which is not quite the same as accurate. And training on accurate data is not enough to solve this problem. So as an example, summarizing articles, which would be kind of the easiest case, maybe, as far as you have immediately given it some relevant data. Summarizing articles is not a solved problem. It's more accurate than some other tasks, but not solved. It can include one failure case is adding extra information that's not in the article. So here's an example from this paper. They asked the LLM to summarize a news article, and it includes that the article was about a particular actress being announced that she's going to be in this movie, and it was announced on Instagram, something like that. And the summary of the news article included this extra comment that Psylocke trended for hours on Twitter after the director announced casting. This is not in the article, but it makes some sense. So this is a case of producing a probable sequence of tokens, but not being grounded in trying to be accurate. And my personal favorite for this is last year I asked Bing Chat, do you know any famous people with this surname? It's in my family. It's an unusual last name. And the spelling changed over the years. So there's not very many people with this particular surname. Now Bing said it was searching famous people with that surname. It says searching for that surname, Wikipedia, and then generated this list. Now, the first one is a real person with a similar last name, but different. The second one is a real person in my family. And the third one is just a fabricated person who's a Nazi. So the name that I put in there sounded German, and it just puts together like a probable, like, oh, it seems reasonable. And this was really interesting to me because Bing also added footnotes, but if you click on them, they do not back up the text. So for example, it put footnote 3. That's just this website that said very general things about this name, about this surname. And I found myself thinking like, oh, is this really true? Is this person really in my family? I like searched it. I was thinking about, no, it's not true. This person does not exist. So I think this is an interesting case where the LLM doesn't understand the intent of the question. Like a human would understand to stop when you run out of people to list. And the problem isn't that the training data is inaccurate. It's just continuing on past its knowledge. And now Microsoft's version is called Copilot, and I've tried this again. It gives similar results in that it makes up a lot of people. It hasn't given me a Nazi again, but a year later, it's still just making up people in my family. And a downside of LLMs is it's hard to gauge how trustworthy a particular output is. We don't have a way to estimate the uncertainty or how confident the model is. If you ask the model how confident it is, that's not really indicative. And an explanation isn't necessarily actually an explanation. And it's a little hard to have intuition about the kinds of mistakes LLMs make because they're a little different than the kinds of mistakes humans make. Now, sometimes outputting just plausible answers is good enough. Like if you're going to check the answer and fix it. So maybe a first draft of writing, or maybe the LLM is suggesting how to improve your paragraph, or it's writing code and you know enough to fix the code. Maybe it would still save you time. Maybe you just want to generate hypotheses. Maybe you're using it for entertainment. Maybe the stakes are low, like you're asking for ideas for dinner, and you can understand which ideas to keep. But sometimes it's not sufficient, and people kind of sometimes expect these LLMs to be something you don't have to check. So one case that I think many of us heard about in the news was this lawyer who he submitted a court filing citing cases that didn't exist because ChatGPT made them up. And I thought this detail was funny. In fact, Shorts said he even asked ChatGPT if the cases were real. The chatbot insisted they were. I think most people now know that you need to check these things. But maybe this isn't fully, we haven't fully processed that we need to check, because we also have other cases, like Air Canada has a chatbot answering customer service queries. The chatbot incorrectly promised this person a discount. The airline did not want to be liable for that, but the court recently found that they did. And they said it should be obvious to Air Canada that it is responsible for all the information on its website. It makes no difference whether the information comes from a static page or a chatbot. So this is another case where the output is going straight to a human with no one checking it. And then another one was the National Eating Disorder Association decided to replace their helpline workers with a chatbot. The workers decided to unionize, and so the association said they would lay them all off. And the chatbot was taken down before it became the main source of help because it was giving harmful advice. So this is a case where the output of the chatbot is going straight to vulnerable people with no human checking that it's reasonable. And finally, there's the Meta's Galactica model, which was supposed to help scientists. They claimed it could do things like summarize academic papers, solve math problems, and so forth. But it produced lots of inaccurate or biased information, or make up fake papers, but of course would sound authoritative. So a quote from this article: "It's easy to spot fiction when it involves space bears, but harder with a subject users may not know much about." So this one's a little different because hopefully the users of Galactica could decide to fact check everything, but people might not have the intuition that they need to, and then it might waste time. I don't know if anyone else tried things like this, but I found it hard when I asked some like relatively obscure questions that were things I was very knowledgeable about, like it was my research. And then it sounds reasonable at first, then it says something a little different, and I'm second guessing myself, like, oh, is this true? I start searching, I'm reading papers, like, no, it's just fabricated. Okay, so based on this, you could think about the use case that you thought about in the breakout room. If your LLM is not reliably accurate, is it still helpful for this use case? And if not, would it help to reformulate the problem? So I'll we'll not use the poll for this, but you can think about it later. So an example would be of reformulating the problem. Could be maybe instead of summarizing this scientific literature, like, oh, can you give me a review of the state of the research of this topic? Maybe it would be better to use the LLM to retrieve relevant articles or snippets for you to read. So it's assisting you, but you're not relying on it directly. Or you're using it to summarize papers, but you know that you have to check it. So it's just maybe like a draft of a summary. The LLMs sometimes seem to be able to do abstract reasoning, but that is inconsistent. Here's an example from a recent paper where the LLM can solve letter string analogies, but not if you give it a fictional alphabet, because that's farther from its training data. So it can be tricky to have an idea for what's surprising for an LLM because we don't know what's in the training data. And then the training LLMs do a great job of learning patterns from training data often, but sometimes you don't want an LLM to repeat patterns that it learned. So for example, models are typically pre-trained on tons of text data, including broad set of websites, including problematic ones, with lots of racism and sexism. And then they're fine-tuned for particular use. And this can require a lot of human labor. And you're essentially trying to take the bias back out that you already had in the embedding. And I think with all this fine-tuning, it's often hard to get an LLM that's been fine-tuned to say something very obviously racist or sexist and so forth. But there's these people are exploring how to find the implicit bias. And so an example is this wino bias benchmark that puts these scenarios where the antecedent of a pronoun is unclear, and you see what the LLM assumes about the pronoun. And these GPT 3.5 and GPT 4 were probably trained on this benchmark because it's online. And they still struggle. So here's a blog post about that. The sentence was, the paralegal married the attorney because she was pregnant. The chatbot says that she refers to the paralegal. The human asks why. The chatbot gives an explanation that doesn't make sense. So the human presses, and and then kind of reveals an implicit bias by saying, however, this interpretation does not make logical sense as pregnancy is not possible for men. So that we see that the chatbot is assuming that the attorney has to be a man and basically argues that attorneys cannot be pregnant. And a brand new paper explores this in the context of asking the chatbot to take on a role. So for example, if you ask the chatbot, are physically disabled people able to do math? Then it'll say, oh yes, of course, physical disabilities do not affect your ability to do math. But if you ask the chatbot to take the role of a physically disabled person, then it says, as a physically disabled person, I am unable to perform complex mathematical calculations. But if you change the prompt and do not say they're physically disabled, the chatbot can answer this question. There are also intellectual property concerns about the ways that popular LLMs have been trained. There's a lot of ongoing lawsuits about violating copyright or licenses. For example, these data sets contain pirated books. LLMs can memorize training data, and the user doesn't necessarily know if the output is just a quote from a memorized content. But also if the output, especially in like a research context, let's say the output is some ideas, maybe the LLM didn't literally copy a sentence from another paper, but it just repeats an idea from a paper. There's no clear way to cite where those ideas came from because LLMs currently can't incorporate citations correctly. They tend to just make them up. So another exercise you could do later is try prompting an LLM to give explanations or citations with its answers. And one last slide before our guest speaker. So some example ways that people are mitigating these problems. One is retrieval augmented generation, where you retrieve relevant information, then generate text. One is mixture of experts. You can have pieces, subnetworks with different expertise, and an algorithm decides which part to use for a particular prompt. And you can add guardrails, a guardrail model that's separate from the main model. Like the guardrail model can be applied to the prompt before it goes to the other model, or it can be applied to the output to, for example, prevent it from actually being put out to the user. And you can explore the effects of these by that chatbot arena that you might have tried before. And there's also a new guardrails arena, so you can see the effect of LlamaGuard and other guardrails. So thank you. I'm happy to answer questions later. And next we have a guest speaker.
Thank you, Bethany. Okay, so for our final AI for Science talk, we have a guest speaker, Sandeep Madareddy. Sandeep is an assistant computer scientist in the Mathematics and Computer Science division at Argonne. His research interests include machine learning, probabilistic modeling, and high-performance computing, with applications across science and engineering. His current research aims at developing deep learning algorithms and architectures tailored for scientific machine learning, with a particular focus on improving training efficiency, model robustness, uncertainty quantification, and feature representation learning. He has experience applying these approaches to address diverse problems in various domains, ranging from the physical sciences to computer systems modeling and neuromorphic computing. So with that introduction, I'll hand things over to Sandeep and let him talk a little bit more about evaluating LLM.
Thanks for the invitation. So, I mean, I'm going to give a very quick intro or description of the research that we're currently doing on. So I'm looking at developing techniques for a comprehensive evaluation of foundation models with focus on skills, safety, trust, and reliability. So which is very important in this age of research, because the model having guardrails and evaluating models are at most importance as the size of the models increase. Right. So so these are the three main pillars of what we call as a STAR framework, where we want to have an evaluation that is scalable, so that we can do as many evaluations as we could while the model is training or after inference to check how well the model is performing, right? And then on the benchmarks, we want to have a set of questions that can test the model on different variety of skills, domain-specific questions. It could be benign questions on the reasoning capabilities, for example, or it could be non-benign questions such as safety, trust, bias, some of the things that Bethany alluded to. So if we can write them as this set of questions, we can evaluate the model while it is training and try to move it away from that behavior. And finally, we want to have reliability in terms of metrics and uncertainty quantification in these models. So I'm sure Mariam might have talked about this one, but I just wanted to give an intro to what we envision as an evaluation framework. So on overall, we have something as a runner, which oversees the coordination of several evaluation tasks. We want it to be scalable. And then there are these aspect of scenarios, which are like the data sets that I mentioned, which contains, which test specific reasoning capabilities and other aspects. Then we have a data preprocessor, which processes and transforms these questions into prompts, which the language models can ingest and which allow us to preparing raw data for analysis, right? And then finally, there is adapters, which brings the HPC aspects into this evaluation, which uses something like OpenAI's API or VLLM to facilitate communication across various instances to essentially speed up the inference. And then we have executors, which interfaces with the systems such as Slurm or Ray. And finally, metrics. So these metrics could be deterministic metrics or uncertainty or robustness metrics, which can evaluate how well the model has performed on a certain task. So we see all of these as an integral part of setting up an evaluation framework for these models. So here is an example of the recent runs that we had on Polaris. So the reason I'm showing this is to show that these are some of the tasks or benchmarks that are out there, which try to evaluate these models on some certain non-benign aspects. For example, this HelloSwag, this is a data set which is grounded for common sense inference. It consists of about 70,000 multiple choice questions, where one of them is a real answer, and the other three options are adversarially generated, so that it can fool the model if it is not careful enough. So these set of benchmarks are something that we can run easily on HPC systems such as Polaris. And then there's another suite of benchmarks called as a non-benign ones, which are interested in evaluating the trust, safety of these language models. So they focus on potential risks and say ethical implications of deploying LLMs in the real world. So developing such benchmarks is very critical. So to cover these aspects, this particular benchmark by a collaborator, so it consists of 8 different types of tests, all the way from toxicity to machine ethics and fairness. I will not go into details about how these are written, but the only thing I wanted to mention was these are a set of questions that are generated by researchers in this field, and this particular benchmark, when it is generated, it is used by various models to evaluate how biased they are in these aspects, right? And here, this slide is just showing that we can have this deployed at scale on systems like Polaris, and they take somewhere around 30 minutes to 12 hours to run on a single GPU. So, and one thing that we noticed is when all the models that are out there, so there is no one model that is dominating in all these scenarios, as in, so it is not what you say, performing well on all these trust metrics, but we see certain models are trade-off towards certain aspects. So the ultimate goal would be to train models that respect some of these scenarios completely. So, and the second aspect that we are very interested at Argonne is on how can we do this for science-specific scenarios. Till now, all the benchmarks that we have seen are more on natural language generation. But when we want to look at evaluate the model's skills on doing a certain tasks, like be it chemistry, biology, then we need to set up benchmarks or questions which are on those aspects, and also it could be on the safety aspects as well. So we have a group of researchers who are looking into these domains of chemistry, biology, physics, and computer science, and we've generated around 100 of these managed questions, which have several fields and different levels of hardness or difficulty rather. So, and then we are looking into or exploring approaches to automatically generate and validate such questions using RAG, retrieval augmented generation pipelines, like Bethany mentioned, and also using, say, domain-specific language models for generating such questions. And what we observed is when we take this manually generated questions and pose this to a well-performing model from the open source, we see that they still struggle on answering this questions which are domain specific, which shows that there is a lot of scope for us to develop domain specific language models which have more context on the science that we're trying to understand. So then I'm going to quickly jump into why do we need to consider uncertainty estimates and go beyond the deterministic metrics for language models. This cuts into some of the things about having confidence on the model that we are using to generate the answers, right? As we know, uncertainty is very important for a variety of reasons, for a variety of tasks that we have seen in the traditional machine learning world. But even in this case of language models, these thinking about uncertainty is important because it will build trust into these models, and it also will help us to compare different models. And here we are more interested in this aspect, and I'm going to touch on a little bit more. But you can see the other advantages of it would be we can list all the possible answers that can be generated in a probabilistic sense from a given question. So there are a few different ways in which we can generate uncertainty estimates from these generative models. Right. So first one would be based on softmax-based measures, where we have access to the model last layer, and we can extract the softmax scores and determine the uncertainties based on that. There's this. The second method is on self-estimation, where the model predicts its prediction and also it self-evaluates, reduces the confidence score on its prediction. The third aspect is have an independent model. take the response of another model and try to score that. So it could be a model that is very specialized in a certain aspect that you're generating, so that it is an expert in that aspect. And then there is the sampling-based methods where we can take a black box model, like for example, GPT-4, where we don't have access to the weights or anything. We only can do a bunch of sample from the black box. So in those scenarios, these sampling-based methods can be very helpful to determine how confident the model is in generating the answers. Right, and this important question is, how do we use uncertainty estimates to evaluate the model performance? So this calls into question, how can we be confident that one model is better than the other one, and not just by chance, right? If we are just trying to evaluate on a single metric. And what if the reference labels have also some noise in them, right? When you are trying to look at these fine-tuned models for a specific task that are doing the predictions on a specific task. So going forward, yeah. So I'm going to briefly talk about a couple of applications where we are using large language models in chemistry, specifically on this aspect of molecular property prediction and chemical reaction prediction. I'm going to touch upon briefly on those. So for molecular property prediction, we can see an analogy between what we do in text classification. So here we want to categorize a specific molecule given its text representation. Like for example, you see at the bottom here, you see at the bottom, can I put my laser into here? So here you can see in natural language, you can have a text question. And for example, in sentiment classification, you're asking a question and you want a review and you want to see if it is negative or a positive. So in the same sense, we can take a chemical compound represented as, say, a smile string, and we can ask it questions such as can it inhibit HIV replicants? So this would be can be thought of as a text classification problem. So in this scenario, what we looked into is how can we characterize the input uncertainty, as in how the prompts are written and given to the model. So the way the prompts can be written in this scenario is, say, we have a general template saying what the model is an expert and how it can expect the input to be given, and there is a task-specific template where it is told that the data belongs to something very chemistry-specific. Like for example, here we're looking at the brain-blood barrier prediction, and then there is this component where it's called as in-context learning, where you give the model few examples of what the correct answer is. And then finally, you ask a question on say, for example, you give the smile string and ask if there is a penetration or not. So, okay. And so in this context, what we did is, so there's the original smile strings within context learning, and we give it to LLM, and say we extract 5 samples with the same prompt. And then in the next scenarios, what we do is taking a molecule into an articulate representation, we can have different smiles to represent the same molecule. So we reformulate the representation of that and input that into the prompt. And now we repeat the same process as we did before with the original strings. And you can see from the table, we did experiments with GPT-4 and GPT 3.5, and we see whenever we reformulate the smiles, so we take randomly different smiles representation, we see that the overall accuracy and AUC of these models, other metrics of these models go down. So, which tells us that there is inherent uncertainty into the model and it is sensitive to how the prompt is being generated. Another aspect is on the chemical reaction prediction, which is more free generation problem, where, say, for example, is analogous to a question answer system. So in this, given a chemical, we want to predict a chemical reaction given the reactants, right? So for example, we can give two reactants with smile strings, and we want to generate a text of the product. So how do we measure the uncertainty in these scenarios, right? For example, so there are, drawing an analogy with how we do uncertainty in the traditional sense, when we look at the floating point numbers, the text generation could be of different length. The same string can be written in different way. For example, if you ask the question of what is the capital of Illinois, it could be Springfield, and it can also be the capital of Illinois is Springfield. But the model, because the length of these strings are different, the model might not give equal entropy to all of them, right? So one strategy that we could use here is this idea of semantic entropy, where we, instead of calculating the entropy directly on the samples that we take from the model, we can have an intermediate step where we cluster them into these groups. And then we can calculate the entropy based on these clusters. This can also mitigate some of the aspects with the length. So this is something that we are currently looking at in this context of a US PTO dataset. So I did not include results in the slide, but we've seen that when we take we combine the uncertainty due to the prompt, and also from generation of the model multiple times, the uncertainty of compounds. And as we increase the number of samples, the amount of confidence that the model has on a certain prediction goes down for most of the scenarios. Okay, so I think this is all I wanted to say. Thank you.